Hi, in this video, we're going to talk about the concepts of general trees. The first thing I want to say is that as with the linked list, if we want to study trees, let's get lots of papers and pen or pencils and be ready to draw lots of pictures. To start with something that is familiar, this is the simplified version of classification of animals that we looked at when we study inheritance. So at the top is just general animals, and then they branch out to vertebrates and invertebrates, and from there they branch out to even more different kinds of animals. So this is one of the many examples of a tree. Now, this is an upside down tree that it's smaller at the top and it fans out and getting bigger as we move from top to bottom, right? And most trees in computer science that we will study, they are like that, upside down trees. So tree is another abstract data type that it acts as a container that can store other types of data. The typical operations that are defined for tree include insertion of data, removal of data, and traversal, which is visiting all the data in a tree, etc. Now, the tree that we'll study in this class is what's called a general tree. It's general in the sense that there is no restriction on the number of children each node can have, and there's no restriction on the order of children. Other trees, such as binary tree or AVL tree, they have rules on the children and the order of children, etc. Now, those other trees that they'll be studied in other classes, such as 3C. But again, in this class, we'll focus on the general tree. So general tree has many different applications. For another example, for those of you who know what folders or directories are on your computer, well, I'm on a Mac, but very similarly for Windows, you can actually view the folder structure on your computer as a tree. So I can run the tree command here, and it shows me right under where I am, my current folder. It has another folder called accounts, address, books, applications, and then inside them, there are further folders or files. And this one is a pretty big tree with lots of folders, very deeply nested. And here is another example of a general tree called a game tree. And this particular game is the one that we're familiar with, tic-tac-toe. So at the top of the tree is a blank board. So we haven't started playing yet. Now, the X player is the one that makes the first move. So the X player can put an X in the middle of the board. So that's a child of the root blank board, and the X player can also place the X in a different position. So that forms another board or another child of the original blank board. And as a matter of fact, there are only three children of the original blank board here, but there are a total of 9, right? There are actually 9 possibilities. So this is not even the full tree. And then now once the X player make a move, then it's the O player, right? So the O player can put a piece here at the corner or in the middle or in a number of other places. And the same thing for a different board where the player X marks this square, and the O player can put the O in other places on the board. So as you can kind of imagine, even for a simple game like tic-tac-toe, this tree becomes very big very fast. And here is one more example of using a general tree to represent an algebraic expression. So this expression at the top level, that's the multiplication. So that's what this node is. Now, the two operands of a of the multiplication is another two expressions. So this one on the left is a division between the sum of 5 plus z and minus 8. So that's what that is. And the second operand to the multiplication is a 4 to the second power. So this is the power operator and the two operands. So very often an expression like this in a programming language such as Python or C++ will be converted to a tree before they are actually evaluated. So to study trees, let's standardize on the terminology. So the first thing we want to look at is the nodes. So trees are composed of different nodes, right? And now there is a very special node, the node at the top of the tree, and that's called the root node. And there is only one root per tree for obvious reasons. Next, there are child nodes and parent node. So the child node of A is B, C, and D, right? All the nodes that's one level directly under the current node. And now the parent node is well the parent, the node that's above the current node. So C would be the parent node of I, J, and K, right? Or an A would be the parent node of B, C, and D. Next is the sibling nodes. So they are the nodes that have the same parent. So I, J, and K, they're siblings because they have a common parent, that is C. And finally, there are these leaf nodes, or the nodes at the kind of the very bottom of the tree, and these nodes do not have any child nodes. And next, there are these things called subtrees. So for example, here, these three nodes, they are a subtree that has the root at the node G. And here is another subtree that has the root at node C. So subtrees are really just smaller trees. And that if that definition sounds a little bit recursive, well, it is. And that foreshadows lots of use of recursions in our tree implementation. Next is the size of a tree, which is the total number of nodes in the tree. So for a tree that has the root at A, if you count the number of nodes, there are 14 nodes. So the size of this tree is 14. Now we can also talk about size of a subtree. So for the subtree with the root at G, the number of nodes is 3, so size of that subtree is 3. And for this subtree, the number of nodes is 4, so the size of the subtree with the root at C is 4. We also talk about the depth of a node. So the depth is the number of levels below the root node of the tree. So for the root itself, well, it's 0th level below itself. So the depth of the root node is at 0, and the children of the root node is at depth 1. The grandchildren are at depth 2, and so on. So the next concept is the height of a node, which is slightly trickier. So the height of a node is the number of levels from that node to the deepest node. So for example, the leaf node always have a height of 0 because, well, it doesn't have any child. So it's just comparing to itself. So it's at height 0. Now, for say node E, the deepest node below E is just L. So, so its height is 1. Now, for B, then the deepest node of B is L, right? It's not F, right? Even though F is one of its children, but B has grandchildren of L, M, and N, and it's 2 levels from the deepest node. So the height of B is 2, and you can apply the same logic to the height of the root node. So the height of this tree is the height of the root node, which is 3. Now, the reason I said this is a slightly trickier concept is because the nodes at the same depth do not necessarily have the same height. So, for example, if we look at this part of the tree, the leaf node I Well, because it's the leaf node, so it has the height of 0, right? And its parent C has a height of 1. Now, so height of C is different from the height of B, which is one of its siblings. And again, that's because it's the height is just the level from that node to the deepest node. And to C, the deepest node is different than the deepest node reachable from B. So be careful with that. And by the same definition, the sibling of C, the D, is itself a leaf node, so it is at height 0. So here are a few exercises for you to make sure you understand the concepts of depth, height, and the size. So please pause the video and give these a try. And here are the answers, and please verify those against yours. So that concludes our introduction to the concept of general tree.